All right, so let's try this one. Again, we're drawing shear force and bending moment diagrams. We have a simple supported beam with a whole bunch of different kind of loads going on. I like to start the same way every time, so we'll begin with finding our reactions. So I'll call this point A. So I'll find the shear at A. There's positive shear at A. I'll call this point B. And there's positive shear at B. So I'm going to use my equations for equilibrium of this free body diagram, which I can do. I only have two unknowns, so I can solve for that. Before I go there, I think it'd be easier to go ahead and resolve that to a concentrated equivalent force for my statics. So it's a rectangle, so base times height. The base is 4 meters, the height is 4 kilonewton per meter. So that'll give me a force, equivalent force of 16 kilonewtons. And applied right in the middle, that would be either 2 meters from either side, whichever way you want to go. So I'm going to come over here, and I don't know why, I'm going to sum moments about B. Doesn't really matter, but I'll do it about B. So by summing moments at B, the shear at B will create no moment, so I'll be able to solve for AY in terms of all the other applied forces. Now again, I'm assuming right-hand rule for my sign convention, so all these loadings that are acting down due to gravity are all going to be what kind of moments? Positive or negative?
Positive.
Positive. So I'll just take them in order. The first one is 4 kilonewtons. That's the force, and the distance is 1 meter. Then I have my concentrated equivalent force. That's 16 kilonewtons. And that distance is 1 meter plus 1 more meter plus 2 meters. That's 4 meters. Then I've got the 8 kilonewton force. And it's located from B. Let's see, 1 plus 1 plus 4 plus 1. That's 7. And all the way down here on the end is my shear, and that's going to create negative moment about A with a moment arm of 2 plus 4 plus 2, 8 meters. So solve for the shear at A.
15.5 kilonewtons.
15.5. That seems reasonable. Anybody else get that? 15.5? Yep. Okay, cool. So 15.5, and that will be kilonewtons, and it should be positive. So we have positive shear at A. And if I sum forces in the y direction now, I should be able to solve for my shear at B. So I'm assuming up is positive, so shear at A is up, shear at B is down. All these other forces are down, so I'll have down 4 kips. The concentrated equivalent, 16 kips, and the other applied, I'm saying kips, but I meant kilonewtons. So I should be able to solve for the shear at B. What is that, 11.5? No, 12.5?
Yeah.
And it should be negative. Is that right?
Yes, sir.
I know it's obvious, but just a reminder, if you don't do your statics right, your shear force and then bending moment diagrams will not come out right either. So don't forget, in the heat of the exam, to look at your reactions and kind of make sure they look reasonable. Now, one thing about this problem that's a little interesting is that if this were 4 kilonewtons, then the loads would be perfectly balanced. And basically half of it would go one side and half of it would go the other side. So if this were 4 kilonewtons, then you have 4 plus 4 is 8, plus 16 is 24. That means 12 to each side. But since this extra 4 over here, most of it goes to A and only a little of it goes to B. So you can see that just from that rationale, I'm expecting at least 12 here and a little bit more. At least 12 here and a good portion of that extra 4. So you can kind of rationalize it a little bit to make sure you're at least in the ballpark. All right, with that said, let's go ahead, and we got a lot of lines to draw for our template. So there's the left edge and the right edge. I've got this applied force 1 meter in. I know something's going to happen there. This distributed loading starts there, so I know something's going to happen there, and then it ends here. I know something's going to happen there. And then I've got again another applied load. So my template's pretty busy. I'll go ahead and show my positive x-axis, my positive shear, and all these values will be in kilonewtons. So let's try to begin drawing our diagram. So what's the shear at A? We found it. It was 15.5. What's the shear at B? 12. Actually, negative 12.5. So I know where I'm starting. I know where I'm ending. Then, of course, our relationships are that the change in shear is the area under the load curve, and that the slope of the shear diagram is equal to the load. You might be getting tired of hearing me say that over and over and over. Hopefully mental muscle memory will kick in and you won't think about it either. You'll just do it. That's the idea. All right, so let's apply this to the first segment here at 1. So if you kind of block all that out and look at just the load on this first little 1 meter, what is the load? 0. You have 0 load. You have no change. So whatever starts at 15.5 will stay at 15.5. And we know the slope is equal to the load. Of course, the load is 0, so I got a 0 slope. So I have constant shear of 15.5 over the first 1 meter. Now what happens as I go from the left side to the right side? How much does my shear change?
8.
Exactly the amount of load, 8. Is that positive or negative? Negative. So what's 15.5 minus 8?
7.5.
So that's 7.5. Now the change in shear over from 1 to 2 meters over this span should be the area of this part of the curve, which is 0. So there is no change. And of course, the slope of that line is given by the load, and the load is 0. So it looks like I have a set of steps going on. Start at 15.5. Right after 1 meter, step down to 7.5. Now what's going to happen between 2 meters and 6 meters? No, the change in shear there is the area of this part of the load curve, which is a rectangle, distributed load, and we already know that that's what? 16. That's minus 16, right? It's negative load. So what's 7.5 minus 16?
Negative 8.5.
This is not, unfortunately, going to be a very good scale. And what's the slope of the shear diagram? It's equal to the load, and the load is constant and negative. So I have a constant negative slope. Look at that. Shear is 0. That might be something important. All right, let's keep going. So what's the change in shear over this 1 meter? Would be the area under the curve on the same meter, which is 0. So that means there's no change. and the slope of that curve is equal to the load. The load is 0, so we have a 0 slope. What happens as I go from the left side to the right side here? Yeah, the shear changes instantaneously how much? 4, and it's down, so it's negative. What's 8.5 minus 4? 12.5. The change in shear over this last 1 meter would be the area under, it's the load curve, area under the load curve, which is 0. That matches. And the slope is the value of the load, which is 0, so it's flat. And there's your shear diagram. What's the maximum shear? 15.5. Where does it occur? At A. But now, since we've got this 0 value for shear, we're going to add that to our diagram, because that's going to come in handy. In fact, if I project that all the way back up to the top, this is the segment that I'm working on. So let's call that, let's see, I'll name that X1. This would also be X1. So let's use our equations here to figure out what X1 is. So what is the change in shear from here to here? Well, we start off at 7.5, we end at 0, so that's a change of minus 7.5. What's the area under the load curve in the same segment? That would be this segment right here. Well, it's a rectangle. Has a base of x1 and a height of 4. So that'd be minus 4x1 kilonewtons. Well, those two things are equal. So you get an equation that says 4x1 is equal to 7.5. So x1 is equal to, what's 7.5 divided by 4? 1 something.
1.875.
Well, that's okay. 1.875, and that would be meters. So if this is 1.875 meters, this section is 4 minus that, or 2.125 meters. We can use those values in just a second. So let's draw our diagram for moment. Positive x, positive moment. All of our values will be in kilonewton meters. Do I know the moment anywhere? What's the moment at this end support? 0. How about over here at B?
0.
Also 0. So again, I know where I'm starting. I know where I'm going to go. So our relationships for this part will be that the change in moment is the area under the shear diagram. And then, of course, the slope of that moment diagram is actually equal to the value of the shear. So again, we have to take it segment by segment. So here's a nice segment. It's a rectangle. It has a base of 1 and a height of 15.5. That's a pretty easy area to calculate. It's 15.5. It's positive. So I'm going to add that to 0, and I'm going to get 15.5. And the slope of that diagram is the shear, and the shear is constant, 15.5, and positive. So there's my positive 15.5 shear. Moment, sorry. Now from 1 to 2 meters, this segment, the change in moment is this area. So I'll kind of hatch that one a little finer so you can see it. That little area there, what's the area of that part of the curve?
7.5.
Yeah, base is 1, height is 7.5. So what's 15.5 plus 7.5?
23.
23. And again, the slope is equal to the shear. The shear value is smaller, 7.5. It's still constant. I didn't really draw it that well, but actually, I did a bad job. So this slope is steeper than that slope. This slope would be 15.5. This slope would be 7.5. I didn't really draw it to scale very well. Okay, now, what's the change over this area? Now, we've already solved for x1. I know this is 1.875 feet, and this side would be 2.125 feet. So what's the area of this triangle? It'd be 1/2 base, 1.875 times height, 7.5. What's that?
7.03.
What is it again?
7.03.
Add that to 23. What do you get?
30.
Oh, how convenient. 30. The slope of the moment diagram is the shear. The shear starts off at a positive slope and decreases to 0. So I have this slope decreasing to 0. All right, let's keep going. So what's the change between here and here? Well, it'll be this part of the rectangle, or the triangle. What is that part? 1/2 base, 2.125, times height, minus 8.5. What's that? Almost 9.
It's -9. I mean, it's 9.
It is exactly 9?
It's 9.03.
Okay, so we subtract that from 30, we get 20. What do we get? 21, right? Roughly. This slope starts at 0 and gets bigger, so it's kind of doing something like that. All right, what's the change from over this next 1 meter? It would be this part of the curve. And that's 1 times negative 8.5. So that's 8.5. So what's 21 minus 8.5?
12.5.
12.5. That slope is constant and negative. And then the final meter, it's this area, which is 1 meter times negative 12.5. 12.5 minus 12.5 gets us back to 0. And the slope is equal to the shear, and again, the shear is constant and negative. So I didn't do a very good job of drawing it, but all of these little straight segments have different slopes, and this is a parabolic section in the middle. So where's the maximum moment?
30.
That's the value. It occurs where? Here, and that would be 1 plus 1 plus 1.87 feet or meters from A, so that would be 3.875. So now you know where the maximum moment is and where it occurs. That's a very doable problem for the exam. Okay. I'll give you some homework. I don't think Mastering Engineering has any shear moment diagrams online, so you'll probably get a set of 3 that you'll have to do on paper. All right, see you Thursday.
It's just like the numbers running so fast. All the ones that are online will have to. Yes, I didn't say